A big part of every single math class is to understand each class of function and how it behaves. So a big part of your Algebra 2 year has been studying parabolas, square root, cube root functions, rational functions. So these are the exponential and logarithmic functions, and we always want to get a sense of what our parent function looks like. Now you can have an infinite number of bases for exponentials and log functions, but the common ones that get used in sciences are either base 2 or base 10, or a special base that is used especially in the sciences called the base e. And we won't do much with base e this year, but it's a big deal next year, so be ready for it if you take the next year or anything beyond this class. So just to notice, I'm going to do some calculations, and remember that a negative exponent simply represents a reciprocal, so 2 to the third is 8, and the negative exponent simply means it's 1/8, not 8. And by the same token, the negative 2 exponent would be 1/4, 1/2, 0. Remember, that's a big deal. If you take any non-zero number and raise it to the power of 0, 2 to the 0 is an important one. We should look at it individually. Anything to the 0 power is 1. And then 2 to the first power is 2. 2 to the second power is 4. Third power is 8. And it gives us some points that we can then choose to go and put on our graph and then see what we think the smooth curve might look like. So I'll zoom in a little bit here, and one of the things that we should note about this, and it's apparent in the table, is that each increment of x causes the value of the function to double. So from -3 to -2, eighth doubles to a quarter, quarter doubles to a half, half doubles to 1, 1 doubles to 2, 2 doubles to 4, 4 doubles to 8. That is a basic characteristic of exponential functions. And remember that an exponent tells you how many factors of your base. So each time you increment x by 1, you have one more power of 2. You have one more doubling. So if you can just remember that, it makes this easy. If 2 to the 0 power is 1, then it doubles to 2, then it doubles to 4, then it doubles to 8. And as I go to the left of 0, if it doubles going to the right, it cuts in half coming back to the left. So 8 becomes 4, 4 becomes 2, 2 becomes 1, 1 becomes a half, half becomes a quarter becomes an eighth. And I could go on further, but if I did, the values would be so small against the x-axis that I wouldn't be able to really distinguish them from the x-axis. So the actual graph would be much closer to the x-axis than what I'm drawing, but I'm just trying to draw a smooth curve. And this is the way that exponentials behave. They stay flat for a really long time, but when they begin to grow, they just zoom away. And you could tell that 8 would become 16, 32, 64, 128. By the time I got to 10, which is the right side of this graph, 2 to the 10th power is 1024. So they grow faster than any other function you've ever experienced. Now, let's talk about the inverse function. So let me clean my workspace up a little bit. And remember that an inverse function simply reverses x and y. It reverses the process. So if the forward function inputs a -3 to make an eighth, then the reverse function starts with the eighth and gives back the -3, starts with the quarter, gives back the -2, half becomes the -1, 1 becomes the 0, 2 becomes the 1, 4 becomes the 2, etc. And if I begin to graph those points, I'll see a really similar shape. The little dotted line there is to remind you that graphically, when I graph a function with its inverse, it's the reflection over the identity line, the y equal x line. So 1/8 -3 is about right there. It's right 1/8 down -3. and then 1/4 negative 2, and 1/2 negative 1, 1, 0, 2, 1, 4, 2, 8, 3. So those are just all the reversal of the coordinates, and that gives us the same shape graph, but now we need to start taking note of a few things. And again, this graph would be so close to the y-axis this time that it would be indistinguishable, so it's really impossible to give an accurate rendering of one of these asymptotic graphs if you're using pen and paper, and even computer screens make it look like the graph is actually on the axis, but it's not. So let's talk about a couple of things. Number one, recognize that there is no power of 2, even at the negative 100th power, that could ever equal 0. 2 to the negative 100 power would be 1 over 2 times 2 times 2 times 2, etc., 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 until I had 100 factors. And you should be able to tell that that would be an extremely small fraction, very close to 0, but there is no power of 2 that can ever make the answer work out to a true 0. So the exponential graph never touches the x-axis, and then its inverse graph never touches the y-axis. So next thing we should talk about is what exactly is the formula for this inverse function. So you've done a couple of things this year about inverse functions, so the first thing we'd like to do is to re-express our original function in terms of y and x. And when I created the inverse table, I switched x and y. That's what I'll do here. Where I used to have a y, I'm going to write an x. Where I used to have an x, I'm going to write a y. But how do I create the y equal form here? And it's really simpler than you think. The log is the exponent, and the exponent is y. The base of the exponential is 2, so the base of the logarithm is 2, and the answer it gives us the x. So this is a basic log graph that we see. Now, what I was saying just a moment ago about the input and output of the exponential function, there is no power that I can't put in for x. So the domain of that exponential function is any x value at all from negative infinity to positive infinity. So I might write it in the interval notation, negative infinity to infinity. But the range is not so easy. The range never reaches 0. The y value will never become 0. But it can grow infinitely large. So the range, the list of y value outputs, could be anything from 0 but never including 0, and to the infinitely large. So when we create the inverse function and we switch x and y, the thing that used to be the domain descriptor is now the range descriptor. So the range is now from negative infinity to positive infinity for the log curve. And its domain is from 0 to infinity. So let me write that correctly. The range description of x values could be anything from 0 to infinity. So looking at that log graph, simply ask yourself, how far left and how far right does that log graph go? And the furthest left it goes is 0, but it never quite touches 0, but it goes infinitely to the right. And then the range is how far down and how far up does that log graph goes. And there's no limit on how far down it will go, and there's no limit on how far up it will go either. So the range is negative infinity to positive infinity. So there's a basic log curve. Now, notice here that the log base was 2, and if you have a log base that's greater than 1, then its powers get increasingly bigger. So this type of a graph here is called a growth function. And the growth function just means that every increment of x from 1 to 2 to 3, etc., causes the y value to progressively get bigger. So if your base is bigger than 1, then you have a growth function. Now, let's do the same thing, but this time let's do it with a base number of a half. So one time, just to remind you, 1/2 to the negative 3 means I need to take the half times the half times the half. That's 3 factors of a half. But then after I get that answer, I'm supposed to flip it. So this would be this would be 1/2 to the third power here. So 1/2 to the negative third power would take this answer and flip it and become a positive 8. So when I begin to substitute my values of x into the equation rule, then at negative 3, I'm going to have the third power of half in reciprocal, that's an 8. And then same reasoning, the negative 2 would give a 4, the negative 1 a 2. The 0, again, anything raised to the 0 power is a 1. The first power of half is a half, the second power of a half is a quarter, and then an eighth. And so if I graph those, I'll see much the same shape that I had a second ago, except now each increment of x causes the value to be cut in half, to be half as big as it was before. So 8 becomes 4, becomes 2, becomes 1, becomes a half, becomes a quarter, becomes an eighth. And at that point it's so small I don't think I can accurately graph the position. So it's an asymptotic graph against the positive x-axis. And then when it comes to these points here, you'll see quite a rapid change. But notice this time that every increment of x causes the y value to cut in half. It's a decreasing function, and so we would call this a decay function. And the classic example of decay would be like radioactive decay. Also, if you metabolize drugs in your body, half of the drug disappears over a given period of time. We'll talk about that more in the applications, but this is called a decay function. So if we're trying to find the graph of the inverse function, we simply reverse the x and the y, and we don't even worry about anything except just reversing the x and the y. We just know that's the fundamental rule, and after we've reversed those x and y's, we can begin to look at the graph to see if we can intuit what it might look like. So x value 8, maybe I'll change colors this time just to make it a little more apparent. X value 8 makes a y value of a negative 3, and then x value of 4 makes a y value of negative 2, and x value of 2 makes a negative 1, x value 1 makes a 0. You can see those same points coming up. It's a little easier to, not easier, it's a little harder to see how that reflection rule works here. But it still is that rule that when I have a function and its inverse graph, both graphed on the same xy coordinate grid, that they are the reflection over that identity line. So I'll do 1 and then erase it. This point here has been reflected to this point here. So you can see that for any point that we chose, that every one of the points from the exponential going to the log curve is reflected over that identity line. Now, let's find out what that particular function might be. And so to find that particular function, we'd remember that our original equation was simply y is equal to 1/2 to the power of x. And just like the previous example, we would simply say the log is the exponent, and the exponent would be the x, and the base would be a half, and I still have it for my inverse until I switch x and y. So when I switch x and y, that would be y is equal to the base 1/2 log of x. Now, one thing to notice is that I could have done this a little bit differently. I could have called my original function, the half is 2 to the negative 1 power, and then the power of power rule, this would just simply become 2 to the negative x power. And so if I had the original as 2 to the negative x, let me see if I can get me a little room up here. If I called my original function y is equal to 2 to the negative x, then I'll switch the x and the y first. I did it last a minute ago, and it doesn't matter which way you do it. But if I switch the x and y now, it would simply be x is equal to 2 to the negative y. And again, I would simply say the log is the exponent, and then the base is 2, and the answer is x, except one of the things I would have to do now, I don't want to see negative y equal, I would like to see y equal. So I could, if I wanted to, call this curve the negative base 2 log of x. That's an interesting thing that happens with exponentials. Now, just to notice, whenever you have a multiplier outside, it changes the vertical directly. So that would be a top-bottom flip. And if you go back and look at the graph that we did above it, this was a base 2 log base 2 log function. And you ought to be able to tell that this green graph in the example below is simply the reflection of the base 2 log over the x-axis. So either one is the same. Now, these are the fundamental rules for transformations for every kind of a function that exists. There is no function that does not obey these rules. So our argument on this function is right here. And so the parent function is that little y is equal to 2 to the x function. But I've translated this one left 3. Remember, that's inside inverse. And I've translated it down 7. So to be able to see what that is going to look like, before we address the domain and range, let's just graph it. I've encouraged you since early this year when we first began to graph to always do this with your graphs. That is, if I say it's going to be left 3, then I'm going to put a little dotted line 3 grids to the left. That's at x equal negative 3. And if its downshift is 7, then I'm going to put a little a horizontal dotted line at y equals 7. Now, this is one of the tricky things about this graph. Many of the graphs that we studied all year long passed through 0, 0. Did you notice that this graph does not pass through 0, 0? At x value 0, the value of this graph is 1, and each increment of x causes the value to double. You got to wrap your mind around that geometry to be able to do what we're about to do here. So this is still a base 2 exponential function, and so here's what I see. It should cross the y-axis 1 above the origin, and then each increment it should double. So I'm talking about the height from this transformed x-axis. It's been shifted down 7. This is a height of 1. My next point will be a height of 2. My next point will be a height of 4. So each increment of x causes the height of the graph to double. So one more increment of x would double. So if this one is 4 grids above, the next one will be 8 grids above, and that would take me up to here. And then one more would be 16 grids above. So along this grid line, I have enough grids to do 16 above. And 16 above would be right here. Notice that I knew I was 7 units below, and 7 plus 9 is 16. Now, as I move to the left, it gets half as big each increment going to the left. So it would be something that would look like that. And your graph hugs against that asymptote and then begins to grow rapidly. So it would look something like this. And of course, you'd never get graded on your artwork, but you would get graded on all those points in the correct spots. And how do you remember the geometry? And the geometry is that exponentials double, or whatever their base number is, for every increment of x. Now there's one thing that you could do, and you might notice that over here, this is an x value of 1 with a y value of 9. So let's just go see if that makes sense. So if I look at my equation and I input an x value of 1, then if I've done my graph correctly, then I should get a y value of a 9. So that's what I saw as this point over here on my graph. So let's see, what is 2 to the 4th power minus 7? Well, 2 to the 4th power is 16. 16 minus 7 is 9. So there's a quick proof that my graph must be correct, because that's what a graph is, a plot of solutions. And solutions make true statements. And when I put an x value of 1 and a y value of 9 into this statement, it's obviously true. Now that we've looked at the graph, let's see if we can state the domain. The domain for all exponentials is from negative infinity to positive infinity. And that will be true. You can just always rest assured that's true. But the range on an exponential, it never quite reaches that asymptote. So the smallest y value is the negative 7, and it never gets to the negative 7, so I use a parenthesis, but there's no limit on how high that graph will go. So let's try it again. This time let's do a base 2 log function. And again, the first thing that we'd want to do is to look at the transformations there. And what I see is that my base function is the base 2 log function, and it's been shifted left 8 and up 4. And again, I would go left 8 and put the little dotted line to show my translation of the xy coordinate axis. And then up 4, I would simply put a horizontal line there. And there's my transformed axis system. Now, just as a broad sweeping graph, I would tell you that log graphs look like this. That's not very accurate though, so let's get some exact points. So the first thing that you have to recognize on all exponential graphs, every exponential graph passes through the point x value 0, y value 1. Because regardless of that base, any base raised to the power of 0 is 1. So what that tells me also is that every log graph will always go through the point 1, 0. Just notice I've switched the x and the y. And for a base 2 log graph, then it's reversed the x and the y. So for each increment of x and the y, each increment of y rather, the x value gets doubled. So that's the geometry that's going to tell me the shape of this thing. It's going to pass through this point here, and each time it gets 1 higher, the x value is going to double. So if I go from a height of 0 to a height of 1, the x value doubled. If I go from a height of 1 to a height of 2, the x value doubles again. And notice when I say the x value, what I'm really talking about is the distance from the 0, 0 point, but we've transformed the 0, 0 point, left 7 down and up 4. So each time my y value gets 1 higher, the x value gets twice as big. So if I go twice as big one more time, that'll put me there. That's 8. And if I double 8, that would be 16. And so that would be all the way over to here. So if I'm coming back left to right, if I reduce the distance away from the origin by half, then it'll increment the y down 1. So 16 to the right becomes 4 to the right, becomes 2 to the right, becomes 1 to the right, becomes 1/2 to the right. And so at 1/2 to the right, I'd have this point here, and then it would be a quarter to the right and an eighth to the right. And again, we'd see that asymptotic behavior begin to manifest. And so this graph would be asymptotic against that vertical line at x equal -8. So let's see if I did my graphs correctly. A correctly drawn graph ought to go border to border as far as you can reach it. So yeah, I did my graphs right. Every time that you draw any kind of a graph, you should always make sure that you show that you have a pattern and extend that pattern all the way to the available border of the grids. So last thing to do is to discuss the domain and the range of this log function. So the domain of a log function is restricted. There's a leftmost point that it goes to. And the leftmost point of this log function is -8, but there's no limit on how far to the right this function goes, so infinity. The range can go infinitely down and infinitely up, so it's -infinity to +infinity. So it's a brand new kind of a graph. I guess we could do what we did a second ago, and we could check a point. So this point here is an x value of 8, also with a y value of 8. That's interesting. So let's just go see if it makes sense. So we're going to take our equation that was y is equal to the base 2 log of x plus 8 plus 4, and we're going to put in an x value of 8 and expect a y value of 8 to come out. So let's see if it works. So the first thing that we're going to do is to add 8 to our x value, and then this would cause us to have the base 2 log of 16, and then I'm going to add 4 to that. The base 2 log of 16 is the is the exponent in base 2 that gives the answer 16. So that would be a 4. And sure enough, 4 plus 4 is equal to 8. So there's the demonstration that my graph is correct, because that's the definition of what a graph is. It's a plot of solution points. So your assignment doesn't have a whole lot of these. It's just got a couple of exponential graphs and a couple of log graphs for you to graph for yourself. Good luck.